Greetings and welcome to my new calculus channel. My name is John Gabriel, and if you'll recall correctly, in the previous video I showed you an interesting understanding of how we got the arithmetic operators such as addition, subtraction, multiplication, and division. So somebody asked me since that time, how do we actually go from arithmetic with magnitudes to arithmetic with numbers? So that's what I'm going to show you now in this video. So let's begin. Now remember, I showed you that if you need to do division or multiplication, you could choose any one of these segments in the circle to be the unit. And that if you had to, for example, choose the green segment, then both division and multiplication is defined. And notice that with magnitudes, you can't have a zero magnitude. So algebra is, in a sense, much weaker than geometry, because algebra simply doesn't have an explanation why you can't divide by zero. But if you look at this particular video that I uploaded, you'll see that this definition works for any and every type of division and multiplication. It doesn't matter whether you're multiplying 3/5 by 1/4 or 8 by 2 or 15,000 by 0.16 or whatever. There's no difference. The approach is exactly the same. So let's see now what happens when we go from magnitudes, which are the distances these lines represent, to numbers. So if we're looking at numbers, first of all, we have to realize that to represent a number, we need both the antecedent and the consequent parts of a ratio, as you see over here, right? So we don't understand 2/3 unless we have two magnitudes, like so. Now, it's very easy to represent any number using this scheme here, where the distance that you're measuring is the antecedent, which is this 2, okay, or this red line rather. And when we measure, initially we'll measure everything in terms of units, so we'll have something like this, right? And we'll call such a ratio we'll say that such a ratio is described by the number 2/1, okay? But when we write it down, it would be 2:1. So we can give these lengths names. But now in algebra, we have a further level of abstraction where we don't actually care about the length of the unit. In other words, we don't have a particular unit of measure. It's simply the abstract unit. Okay, so first of all, we define number as a magnitude, as the measure of a magnitude. Okay, we define number as the measure of a magnitude, or the size of a magnitude. So once we've named our segments, and we don't have to care about equivalent ratios, because in terms of algebra, equivalent ratios are equal. So for example, it doesn't matter if you have another ratio like 8/8 and 2/2. These are the same in algebra. They're not the same in geometry, because here we are measuring the antecedent 8, and here we're measuring the antecedent 2. If you go back here and look at this scheme here, not that one, this one, you'll see that if we said one like that, then we'd be measuring 1 and 1 like this, or rather, put that over there, and that approximately 1 here, okay? So this would be the way you would represent the numbers. And once you've gotten to that stage, then you can move ahead and define addition and subtraction. So the easiest way to do this is to write down the antecedent and consequent parts of the ratio. So with this pink line, I'm going to write down 1 and 1/3, right, like that. And for the 2/4, I'm going to write 2 and 1/4. Now we have to be able to add those, as we saw in book 5, proposition 12. If we have similar triangles, we can just go ahead and add these parts. Like, so for example, if I add 2 plus 4 and 3 plus 6, they're equivalent fractions. In other words, if I say 2 over 3, that's the same as 6 over 9, isn't it? Okay. Right. Now, so here's how we do it. We can only add them if we translate both of them to the same unit. So for the third, it becomes 4 twelfths. Okay, 4 twelfths. And for the 2 quarters, represented by this brown segment, 2 quarters, it becomes 6 twelfths, right? And now we're in a position simply to add each to each other. So if we took this length here and stacked it on top of the red one, we'd get 10. And likewise, if we took this length here, the blue length along this side, and the red length, the pink and the, I'm sorry, let me repeat that slide. If we took the pink length and the brown length and we added them, then we'd get this final green line here, okay, because it's 4 twelfths and 6 twelfths. So all we'd be doing is we'd be adding the antecedents, which are what we are measuring. And so now that gives us the method to add and subtract fractions, okay? And then similarly, we move on to the quotient and multiplication operations, as you see over here. So a quotient PS over QR is simply this expression here. In other words, it's this added n times and this added n times. And of course, if you wanted to divide 4/5 by 8/10, then this is how you would do it, right? And it doesn't matter whether you choose n to be q or s, it will still give you the same result. And so because the product is defined in terms of multiplication, we use the same procedure, except that we flip the previous two. Because what is multiplication or a product? It's just the quotient with either positive number, measuring the quotient with either positive numbers using the reciprocal of the other. So it should come as no surprise then that we use division to define multiplication, because division comes before multiplication. And what comes before division? That's right, addition and subtraction. And of course, before addition comes subtraction. Okay, so the difference or subtraction operator is the very first that you have. And so this is how you transition from talking about magnitudes here without numbers, okay, without numbers, to magnitudes, to numbers, because you define a number to be a name given to the measure, okay, a name given to the measure of, or a measure that describes the magnitude that is being presented. So for example, 1/2 describes this antecedent, or the measure of this antecedent 1, okay? You could have done it the other way too, by the way. You could have looked at it from the perspective of the consequent, but that's not how it was done. So that's pretty much how you get from magnitudes to number. And note that although this scheme shows you using an actual unit, in this case 3 or whatever, 2 or 5 or whatever the case might be, in algebra we don't care too much about the size of the abstract unit, okay? We don't care at all about the abstract unit. So for example, if we're going to write 1, 2, 3, it's understood that they're all measured in terms of the abstract unit. So I'll include a link to an article, a very well-written article, that explains these details. It's called Discovering the Concept of Number, A Personal Journey. And unfortunately, you'll have to ask me to download it because Google has this new security feature. And that's pretty much all I have. So I hope this answers the question of how we go from magnitude to number. I'm John Gabriel. This is a New Calculus channel. Till next time, goodbye.